Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey begins with a question that sounds simple at first, but becomes more mysterious the longer you sit with it. It is a question about the universe, about life, and about the strange silence that surrounds us in the vast ocean of space. Before we wander too far into the stars, take a moment to settle in. Perhaps the room is dim, perhaps the day has been long, and perhaps your mind is ready for something calm and gently curious. If you feel comfortable, let your breathing slow a little. There is no hurry here. The universe, after all, has been taking its time for billions of years. Let's begin by picturing our cosmic neighborhood. Our home galaxy, the Milky Way, is a vast spiral of stars slowly turning through the darkness. If you could step far enough away to see it from the outside, it would appear as a soft, glowing whirlpool of light with long arms of stars stretching outward like luminous rivers. Within those arms are hundreds of billions of suns, not millions, not a few scattered lights, but hundreds of billions. Each of those stars is a potential center of a planetary system. And over the past few decades, astronomers have learned something remarkable. Planets appear to be extremely common. In fact, it now seems that most stars likely host planets of their own. Some of those planets are giant worlds made of gas. Others are frozen spheres of rock. And some may be more familiar, rocky planets with oceans, clouds, and skies. When you start to think about the numbers, it becomes quietly astonishing. Our galaxy alone may contain hundreds of billions of planets. Among them, many billions may exist at distances from their stars where liquid water could remain stable on the surface. And where there is liquid water, scientists often say, there is at least the possibility of life. Now, imagine that scene for a moment. A galaxy filled with stars. Around many of those stars, planets. Around some of those planets, perhaps oceans. Around some of those oceans, perhaps life slowly stirring, growing, evolving and adapting over long stretches of time. And time, in this cosmic story, is abundant. The Milky Way galaxy is more than 10 billion years old. Long before our own sun formed, generations of stars had already lived and died. Long before Earth cooled into a blue planet with oceans, entire stellar civilizations of atoms and elements had already been forged in ancient stars and scattered across the galaxy. In other words, the universe has had plenty of time to experiment. If life can arise on planets, then it may have had billions of years to do so. If intelligence can evolve from simple life, then perhaps that has happened many times. And if intelligent beings eventually develop technology, curiosity, and the desire to explore, then it is not unreasonable to imagine that somewhere, at some time, a civilization might look out at the stars and begin the slow process of reaching toward them. When you place all those pieces together, something curious begins to emerge. With so many stars, so many planets, and so much time, it seems quite plausible that the galaxy could contain not just one technological civilization, but many, perhaps scattered like distant islands of awareness across the cosmic sea. And yet, when we look out into the sky with our telescopes and our radio antennas, we do not see clear signs of such civilizations. We do not see enormous structures surrounding distant stars. We do not detect powerful artificial signals echoing through space. We do not observe fleets of interstellar travelers crossing the galaxy. Instead, the universe appears quiet. Not empty, of course. The cosmos is full of extraordinary things. Pulsars ticking like cosmic clocks, nebulae glowing with newborn stars, galaxies colliding slowly over millions of years. The universe is rich with motion and beauty. But when it comes to unmistakable signs of other technological civilizations, the sky seems strangely silent. This quietness has puzzled scientists for decades. If the conditions for life are common, and if the galaxy is ancient, why do we not see evidence of advanced societies expanding through space? Why does the universe appear, at least so far, to be a vast wilderness of stars with no obvious neighbours calling across the dark? This puzzle has become one of the most intriguing questions in modern astronomy and cosmology. Some scientists describe it simply as the question of cosmic loneliness. Others give it a more formal name, one that we will explore gently as our story unfolds. But for now, it is enough to hold on to the mystery itself. Imagine standing on the shore of a vast ocean at night. Across the water lie countless islands, far beyond the horizon. If those islands were inhabited, you might expect to see distant lights flickering in the darkness. Perhaps the faint glow of a lantern, or the distant sound of voices carried by the wind. But instead, the ocean remains quiet. No lights, no signals, only the soft rhythm of waves and the endless stretch of darkness. The Milky Way can sometimes feel a little like that ocean. Hundreds of billions of stars, each a possible island in the cosmic night. And yet, so far as we can tell, the waters between them remain still and silent. This silence does not necessarily mean that we are alone. It may simply mean that the universe is more subtle, more complex, or more mysterious than we currently understand. And as we continue this quiet journey together, we will explore some of the possibilities that scientists have proposed. Some of them are comforting, some of them are unsettling, and one of them leads to a particularly haunting idea about the fate of intelligent civilizations. But for now, let your thoughts drift among the stars for a moment. The galaxy is vast, ancient, and filled with countless worlds. Somewhere within that great spiral of light, the story of life has been unfolding for billions of years. And the question of whether we are alone or simply early remains one of the most peaceful and unsettling mysteries in the entire universe. The quiet question that now sits at the centre of our story did not begin in an observatory or in front of a powerful telescope. It began, rather unexpectedly, during a casual lunchtime conversation. In the summer of 1950, a small group of physicists gathered together at Los Alamos in New Mexico. These were scientists who spent their days thinking about some of the most powerful ideas in modern physics, from nuclear reactions to the structure of the universe. But like many scientists, they also enjoyed wandering conversations during lunch, where curiosity could drift in unexpected directions. One of those physicists was Enrico Fermi, an Italian-born scientist known for his clear thinking and remarkable ability to simplify complex problems. During that lunch, the conversation turned toward a topic that had been appearing more often in newspapers and science fiction stories at the time: flying saucers and the possibility of alien visitors. The discussion moved lightly from one idea to another. Someone joked about interstellar travel. Another wondered how advanced an alien civilization might become if it had enough time to develop its technology. It was the kind of speculative conversation that often appears when curious minds gather together around a table. And then, at some point in the conversation, Fermi paused and asked a very simple question. Where is everybody? At first glance, the question sounds almost playful, but the more you think about it, the deeper it becomes. Fermi was not asking about aliens in a casual sense. He was thinking about something much more fundamental. If the universe is vast, and if the conditions for life appear in many places, then intelligent civilizations might not be incredibly rare. Given enough time, some of those civilizations might become technologically advanced, and if a civilization becomes advanced enough, it might begin exploring the stars. Now consider the amount of time available for such exploration. The Milky Way galaxy is more than 10 billion years old. Our own sun, by comparison, is about 4.5 billion years old. That means the galaxy had already existed for billions of years before Earth even formed. During those earlier ages, many other stars and planets would have already been present, quietly orbiting their suns in the darkness of space. If life could arise on some of those worlds, and if intelligence could eventually emerge, then it is possible that technological civilizations might have appeared long before humanity ever looked up at the sky. And if even one civilization had begun exploring the galaxy millions of years ago, the results might be difficult to miss. To understand why, imagine the pace of exploration spreading outward from one star system to the next. Even if spacecraft travelled slowly compared to the speed of light, a civilization could still expand gradually, moving from one nearby star to another. Each new colony might eventually send its own explorers onward, continuing the process. Over extremely long periods of time, this kind of expansion could ripple outward through the galaxy like gentle waves across a lake. Even if the process was slow, the galaxy itself is enormous in age. Millions of years would pass easily. Tens of millions of years would pass almost unnoticed on cosmic timescales. Over such spans of time, a civilization might slowly spread across large regions of the galaxy, and yet when we look outward today, we do not see clear signs of such widespread activity. No unmistakable alien spacecraft have arrived in our solar system. No massive engineering structures have been detected surrounding distant stars. No steady chorus of artificial signals has been heard echoing across the sky. Instead, the stars continue their quiet motion, the galaxies drift slowly apart, and the night sky appears calm and natural. This contrast between expectation and observation is what gives the question its unusual power. If intelligent life should be common, then we might expect the galaxy to look busy. We might expect to see traces of advanced civilizations shaping their environments, building enormous structures, or sending signals across the stars. But instead, the universe appears strangely quiet. Over time, scientists began referring to this puzzle with a simple name. The Fermi Paradox is not really a paradox in the strict mathematical sense. There is no logical contradiction hidden within the laws of physics. Rather, it is a tension between two ideas that seem reasonable when considered separately. On one hand, the universe appears capable of producing life. Planets are common, and chemistry can be remarkably creative when given enough time. The basic ingredients for life seem to exist throughout the cosmos. On the other hand, if intelligent civilizations arise and develop technology, they might eventually become visible across large distances. But so far, the sky does not reveal such civilizations. Some scientists describe this situation as the Great Silence. It is the silence of a galaxy that appears full of opportunity for life, yet does not obviously display the presence of technological neighbours. There are many possible explanations for this silence. Some of them suggest that life itself may be extremely rare. Others propose that intelligent civilizations tend to appear briefly and then disappear again. And still others suggest that advanced societies might deliberately remain quiet, avoiding attention in a vast and potentially dangerous universe. Each of these possibilities leads us down a different path of speculation. Some paths are comforting, suggesting that intelligent life may simply be scattered thinly across the cosmos. Others are more unsettling, hinting that something may prevent civilizations from surviving long enough to spread among the stars. As we continue this quiet journey through the ideas surrounding the Fermi Paradox, we will gradually explore these possibilities one by one. Along the way, we will encounter concepts that blend astronomy, biology, and the long history of evolution. And somewhere within that chain of ideas lies a particularly haunting possibility, one that scientists sometimes refer to as the Great Filter. But before we reach that idea, we will first explore a simpler question. If the galaxy contains so many stars and planets, how many civilizations might we actually expect to exist? To approach that question, Scientists once tried to construct a kind of cosmic estimate, a way of thinking about the many steps that must occur between the formation of stars and the appearance of intelligent beings capable of looking up at the night sky. And that gentle attempt to estimate our possible neighbours brings us to the next part of our story. By the time scientists began seriously thinking about Enrico Fermi's quiet question, another curiosity naturally followed behind it. If the galaxy is filled with stars and planets, perhaps it is possible, at least roughly, to estimate how many civilizations might exist out there. Not an exact number, of course. The universe rarely gives us neat answers. But perhaps we could build a kind of thoughtful guess, something like a chain of probability stretching from the birth of stars to the rise of intelligent beings. In the early 1960s, an astronomer named Frank Drake proposed exactly that kind of approach. Drake was deeply interested in the possibility of communicating with extraterrestrial civilizations. At the time, radio telescopes were becoming powerful enough to listen for faint signals coming from distant stars. The idea was simple and beautiful. If another civilization somewhere in the galaxy had discovered radio technology, perhaps its signals might still be travelling quietly through space. But before searching for such signals, Drake realised something interesting. To think about alien civilizations seriously, we first needed a way to estimate how many might exist. So he created a framework, not really a rigid equation to be solved, but more like a list of questions that guide our thinking. Imagine you were trying to estimate how many cafes might exist in a large city you've never visited. You might begin by asking a few simple questions. How large is the city? How many neighbourhoods does it contain? How many people live in each neighbourhood? And how likely is it that people in those neighbourhoods enjoy drinking coffee? Each question narrows the possibilities a little further. Frank Drake approached the galaxy in a similar way. He began with the most basic question. How often do new stars form in our galaxy? Stars are the starting point of planetary systems, so the rate at which stars appear gives us the first step in the chain. Next comes the question of planets. For a long time, astronomers did not know whether planets were common or rare, but today we know that planets appear to be extremely widespread. Many stars host entire families of worlds, some rocky, some icy, some wrapped in thick clouds of gas. Among those many planets, the next question becomes more specific. How many might exist in regions where conditions could allow liquid water to remain on the surface? Scientists sometimes refer to this region around a star as a habitable zone, a comfortable distance where temperatures may allow oceans to exist rather than freezing solid or boiling away. From there, the questions become even more delicate. On how many of those potentially habitable planets does life actually begin? Chemistry can be surprisingly creative, but the origin of life remains one of the great mysteries of science. We know that life appeared on Earth quite early in its history, but we do not yet know how easy or difficult that step truly is. Even if simple life begins, another question appears. How often does life become complex? For most of Earth's history, our planet was inhabited only by microscopic organisms drifting through ancient oceans. Complex organisms, creatures with specialized cells and tissues, took billions of years to evolve. Intelligence, in the sense of beings capable of building technology and reflecting on the universe, appeared only very recently in that long story. And even when intelligence appears, the chain of possibilities continues. How many intelligent species develop technologies powerful enough to communicate across space? How many build radio transmitters or other detectable signals? And perhaps most intriguingly, how long do such civilizations last before fading away, changing form, or falling silent? Each of these questions represents a small gateway in the long path from stars to civilizations. The idea behind Drake's approach was not to calculate a precise number. Instead, It helps scientists understand the many uncertain steps that connect the formation of stars with the appearance of technological societies. Some of those steps may be common, others may be extremely rare. If even one of those stages turns out to be extraordinarily unlikely, then the number of civilizations in the galaxy could shrink dramatically. On the other hand, if many of those stages occur frequently, then the galaxy might be filled with life at different stages of development. The Drake framework therefore acts less like a mathematical machine and more like a map of questions. It reminds us that the journey from cosmic dust to thinking minds involves many layers of complexity. Stars must form, planets must gather from swirling disks of gas and rock, chemistry must somehow awaken into life. Life must survive long enough to become complex, and intelligence must emerge, curious enough to look outward and ask questions about the universe. When you pause and reflect on this chain, it begins to feel almost miraculous. Our own planet has passed through every step in that sequence, from the formation of our sun billions of years ago, to the slow emergence of oceans and microbes, to the rise of animals, forests, and eventually human civilization capable of building telescopes and radio antennas. Each of those transitions took immense stretches of time. Billions of years passed while life slowly experimented with new forms. Entire eras of geological change unfolded before intelligence appeared. And now, only in the very recent past of cosmic history, a species on one small planet has begun listening to the stars. Frank Drake's framework invites us to imagine that similar stories might be unfolding elsewhere in the galaxy. Perhaps on distant worlds, other civilizations are slowly emerging from their own evolutionary journeys. Some may be young, just beginning to develop technology. Others might be far older than humanity. But when we combine this hopeful possibility with Fermi's simple question, where is everybody?, the mystery grows deeper. If many civilizations should exist, then the galaxy might already be filled with signals, travelers, or distant engineering projects. Yet the night sky still appears quiet. This tension between expectation and observation is what drives scientists to search for new explanations. Perhaps civilizations are incredibly rare. Perhaps they appear briefly and then vanish. Or perhaps something in the long chain from stars to intelligence acts as a powerful bottleneck, preventing most worlds from reaching the stage where they can explore the galaxy. As we continue this journey, we will begin exploring those possibilities. Some explanations lie in the immense distances between the stars. Others may lie in the delicate balance required for life to evolve, and still others may involve the strange and sometimes fragile nature of technological civilizations themselves. For now, it is enough to remember that the Drake framework does not solve the mystery of the silent galaxy. Instead, it illuminates the path that leads to it, a path made of many small steps, stretching from the birth of stars to the quiet moment when a civilization finally turns its gaze toward the sky and begins to wonder who else might be out there. And the deeper we follow that path, the more intriguing the silence of the universe becomes. When we begin thinking about life beyond Earth, our imagination often moves quickly. We picture spacecraft crossing the galaxy, civilizations greeting one another among the stars, or signals travelling effortlessly through space. But one of the quiet realities of the universe is that space itself is astonishingly vast. To understand why the galaxy might remain silent, it helps to pause and appreciate just how far apart the stars really are. Our own nearest stellar neighbour is a small star called Proxima Centauri. Even though it is the closest star to the Sun, the distance between us and that faint red light is immense. Light itself, the fastest thing in the universe, takes more than 4 years to travel from Proxima Centauri to Earth. Light moves incredibly quickly. In a single second, it can circle our planet more than 7 times. Yet even at that extraordinary speed, it still needs years to cross the relatively short distance between neighbouring stars. Now imagine trying to travel that same distance with a spacecraft. Even the fastest probes humans have ever built move far slower than light. A journey to the nearest star using current technology would take tens of thousands of years. Entire human civilizations could rise and fall during such a voyage. This enormous separation between stars means that the galaxy is not a crowded neighbourhood. Instead, it resembles a vast cosmic archipelago, an ocean of darkness dotted with distant islands of light. If intelligent civilizations exist on some of those islands, they may be separated by distances so great that communication becomes extremely difficult. Consider how signals behave when they travel across space. When a radio transmission leaves a planet, it spreads outward in all directions. As it travels farther and farther, the signal becomes weaker, like ripples expanding across a calm lake. The farther the ripples move from their origin, the more their energy spreads out across a wider area. By the time such a signal has crossed dozens or hundreds of light years, it may become so faint that even very sensitive instruments struggle to detect it. This means that even if another civilization were transmitting signals similar to our own radio broadcasts, we might not easily notice them unless we were listening very carefully and at exactly the right frequency. Distance also affects the possibility of travel. Suppose an advanced civilization developed spacecraft capable of travelling between stars. Even then, the journey would likely be slow compared to the speed of light. Crossing the galaxy in a single leap would be enormously difficult. Instead, explorers might travel gradually, moving from one nearby star system to the next over very long periods of time. Imagine a series of explorers departing from their home star and travelling to the closest neighbouring system. After settling there, their descendants might eventually send out their own explorers to another nearby star, and then another, slowly expanding outward through the galaxy. In this way, exploration could spread across space like a chain of distant voyages rather than a single sweeping journey. But even this gradual process might take an extraordinary amount of time. The Milky Way galaxy is roughly 100,000 light-years across. Even if spacecraft travelled steadily between stars, colonizing one system after another, the full expansion across the galaxy could still require millions of years. On human timescales, millions of years feels almost unimaginable. Entire species can evolve or disappear in such spans of time. Continents shift, climates change, and ecosystems transform. Yet on cosmic timescales, millions of years are surprisingly brief. Remember that the galaxy itself has existed for more than 10 billion years. If even one civilization had begun spreading outward through space a few million years ago, it might have had plenty of time to explore a large portion of the galaxy by now. This observation brings us gently back to the mystery we began with. If intelligent civilizations exist and if they are capable of exploring nearby stars, then the galaxy might eventually become interconnected through slow waves of exploration. Over long periods of time, explorers could move outward step by step, linking distant star systems like beads on an enormous cosmic necklace. But when we look out into the universe, we do not yet see clear evidence that such exploration has occurred. The stars continue their quiet journeys. Planets orbit silently around distant suns. The galaxy turns slowly through space, but no obvious signs of widespread interstellar activity appear in our observations. Perhaps this means that civilizations are extremely rare. Perhaps intelligent species appear only occasionally and remain separated by distances too large to bridge. Or perhaps something else is happening. It is possible that civilizations may exist and even travel among the stars, yet remain difficult for us to detect. Their technologies might be subtle, quiet, or very different from our own. signals may be too faint, too brief, or directed away from us. In other words, the silence we observe may not mean that the galaxy is empty. It may simply mean that space is very large, and that the islands of intelligence within it are scattered far apart across a dark cosmic sea. Understanding this vast scale helps soften the mystery of the Fermi question. The universe is not a small room where neighbours easily hear one another. It is more like a vast ocean where distant ships may sail for years without ever crossing paths. Yet the story does not end with distance alone, because even though the galaxy is immense, there are still ideas that suggest civilizations could spread much farther than we might expect. Some scientists have imagined technologies that allow exploration to expand outward steadily, multiplying as it goes. And when we consider those possibilities, the quietness of the universe becomes even more intriguing, because if such expansion were possible, then the galaxy might not remain silent forever, and the absence of clear evidence begins to feel less like a simple matter of distance and more like a deeper mystery waiting to be understood. When we reflect on the enormous distances between the stars, it becomes easier to imagine why civilizations might remain isolated. The galaxy is vast, and even light itself takes years to cross the small spaces between neighbouring suns. Yet some scientists have pointed out an interesting possibility. Even if interstellar travel is slow and difficult, a civilization might still find ways to explore the galaxy gradually over long periods of time. The idea begins with something very simple: machines. Imagine a robotic spacecraft designed not just to travel to another star system, but also to build copies of itself once it arrives. At first this may sound like science fiction, but the basic principle is not as strange as it appears. On Earth, we already build machines that manufacture other machines. Entire factories operate through automated systems, assembling complex objects with very little human intervention. Now imagine extending that idea into space. A civilization might launch a robotic explorer toward a nearby star. The journey could take many decades or perhaps centuries, but machines do not grow tired and they do not need air, food, or comfortable temperatures. A carefully designed probe could travel quietly through interstellar space until it finally arrived in another planetary system. Once there, the probe might begin a new task. Using materials found on asteroids, moons, or rocky planets, it could construct additional machines. Those new machines could then be sent outward to neighbouring stars, repeating the same process again and again. In this way, exploration could grow gradually over time. One probe becomes 2, 2 become 4, 4 become 8. Each new generation of explorers would continue the outward journey, spreading slowly from star to star. Over long periods of time, this pattern of exploration could expand across enormous regions of the galaxy. Scientists sometimes describe this concept using the term self-replicating probes. The name simply means machines capable of reproducing themselves using local resources. But we can imagine the process in a gentler way. Picture seeds carried by the wind across a vast forest. When one seed lands in a fertile place, it grows into a new tree. That tree eventually releases more seeds, which drift outward to new locations. Over many seasons, the forest slowly spreads across the landscape. In a similar way, robotic explorers could spread through the galaxy like drifting seeds of curiosity. What makes this idea particularly intriguing is the timescale involved. Even if each journey between neighbouring stars required thousands of years, the expansion could still continue steadily outward. Every newly reached star system becomes a launching point for the next generation of explorers. Over millions of years, the process could cover enormous distances. And although millions of years sound unimaginably long from a human perspective, they are relatively brief in cosmic terms. remember that the Milky Way galaxy has existed for more than 10 billion years. Compared with that immense span of time, millions of years pass almost like the slow turning of a page. If a technological civilization had begun sending out self-replicating probes a few million years ago, it is possible that their explorers could have reached a very large portion of the galaxy by now. Some scientists have even suggested that, given enough time, such machines might eventually visit nearly every star system in the Milky Way. This idea leads to a fascinating twist in the mystery we have been exploring. If self-replicating exploration is possible, then the galaxy might not remain quiet for very long once a civilization becomes technologically advanced. Even if intelligent societies are rare, a single civilization with the ability to launch such explorers might eventually spread evidence of its presence throughout the galaxy. And yet, when we observe the sky, we do not see clear signs of such activity. Our telescopes have not detected vast networks of robotic machines moving between stars. We have not observed alien probes arriving in large numbers within our solar system. The planets and asteroids around us appear natural and undisturbed. Of course, it is possible that such probes exist but are extremely small or carefully hidden. A machine the size of a modest spacecraft could remain unnoticed in the enormous spaces between planets. But the larger idea remains intriguing. If exploration through self-replicating probes is possible, and if even a single civilization had begun such a project millions of years ago, we might expect the galaxy to look different. We might expect to see signs of widespread exploration, traces of distant engineering, or unusual activity around some stars. Instead, the universe continues to appear calm and natural. This observation strengthens the mystery behind the quiet galaxy. Perhaps civilizations rarely reach the technological stage where such machines can be built. Perhaps advanced societies lose interest in exploration. Or perhaps something prevents civilizations from surviving long enough to begin spreading across the stars. Each of these possibilities points toward deeper questions about the nature of intelligence, technology, and the fragile balance required for civilizations to endure. The concept of self-replicating explorers therefore adds another layer to the puzzle. It reminds us that the silence of the universe cannot be explained only by distance. Even in a vast galaxy, patient exploration could slowly connect distant star systems over long periods of time, and if that process has not happened, or has left no visible traces, then perhaps something in the long journey from life to advanced civilization is far more difficult than we imagine. As our exploration of this mystery continues, we will begin to consider another possibility. Maybe the problem is not distance or technology at all. Perhaps the true challenge lies much earlier in the story, in the delicate conditions required for life itself to evolve and survive for billions of years. Because the path from simple chemistry to intelligent beings may be far more fragile than it first appears, and if that path is rarely completed, the quietness of the galaxy may begin to make a little more sense. By now, the quiet puzzle of the universe has begun to take a more intriguing shape. On one side of the story, we have a galaxy filled with stars and planets. Many of those planets may have existed for billions of years, offering long stretches of time during which life might begin and evolve. On the other side of the story, we have ideas suggesting that exploration across the stars, while difficult, may still be possible over very long periods. Slow voyages could connect nearby stars. Robotic explorers could travel patiently through interstellar space. Self-replicating machines could even multiply and spread outward over many generations. Taken together, these ideas suggest something rather surprising. Even if intelligent civilizations were extremely rare, it might take only one sufficiently advanced society to begin a gradual process of exploration that eventually reaches a large portion of the galaxy. Yet when we look outward from our small planet, the stars still appear peaceful and untouched. No fleets of ancient probes drift through the solar system. No artificial beacons shine from distant star systems. No unmistakable structures surround nearby suns. Instead, everything appears natural. The planets follow their quiet orbits. Asteroids tumble slowly through space. The distant stars glow with the soft light of nuclear fusion, just as physics predicts. This absence of obvious activity creates a curious tension in our understanding of the universe. If the galaxy is old and life is possible, then civilizations might have had plenty of time to develop technology. And if technology can eventually lead to exploration across the stars, then the galaxy might show signs of that exploration. But those signs remain elusive. One possible explanation is that civilizations may not actually attempt large-scale exploration. Perhaps intelligent beings eventually turn their attention inward, focusing on their own worlds rather than spreading outward across space. Imagine a society that discovers advanced computing, virtual environments, and powerful energy systems. Instead of building enormous fleets of spacecraft, such a civilization might choose to create rich digital worlds or peaceful planetary habitats. For them, the desire to expand across the galaxy might fade. Exploration might remain an interesting idea, but not an urgent priority. Another possibility is that civilizations explore quietly, leaving only subtle traces behind. Advanced technology does not necessarily need to be loud or dramatic. Over time, engineering tends to become more efficient and less wasteful. Machines become smaller, quieter, and more precise. If alien technology followed a similar path it might operate almost invisibly against, the enormous background of natural cosmic processes. A probe drifting through interstellar space might be no larger than a modest spacecraft. A scientific station orbiting a distant star could be hidden among natural asteroids. Signals might be carefully directed towards specific destinations rather than broadcast widely across the galaxy. In that case, the silence we observe might simply reflect the limitations of our own detection methods. Our telescopes and radio antennas are impressive instruments, but they have only begun listening to the sky during the past century, a very short moment compared with the age of the galaxy. Imagine trying to detect distant ships on a vast ocean while listening for only a few minutes each night. It would not be surprising if many voyages passed unnoticed. There's also another possibility, one that some scientists consider both fascinating and unsettling. Perhaps civilizations rarely survive long enough to begin exploring the galaxy at all. The path from simple life to advanced technology may involve many delicate steps. A planet must remain stable for immense stretches of time. Life must evolve complexity and intelligence, and a technological civilization must learn how to manage the powerful tools it creates. If any part of this chain breaks, the process might stop before reaching the stage where interstellar exploration becomes possible. In that case, the silence of the galaxy would not necessarily mean that life never appears. It might mean that civilizations tend to remain fragile, appearing briefly before fading away. This idea begins to shift our attention away from the distances between stars and toward the long story of life itself. Because the journey from chemistry to consciousness is not a simple one. On Earth, it took billions of years for life to evolve from microscopic organisms into complex creatures capable of thought, language, and technology. Entire ages of biological experimentation unfolded before intelligence finally appeared. If even one of those steps is extremely unlikely, then the number of civilizations in the galaxy might become very small. And if the later stages of technological development prove unstable, civilizations might rarely survive long enough to leave visible traces in the cosmos. These possibilities bring us closer to a concept that scientists sometimes call the Great Filter. The Great Filter is not a physical barrier like a wall in space. Instead, it represents a stage in the long chain of cosmic evolution that is extremely difficult to pass. Perhaps the filter lies in the origin of life itself. Perhaps it appears during the emergence of complex organisms, or perhaps it waits in the future of technological civilizations, testing whether intelligent societies can survive the immense powers they create. Wherever that filter may lie, it could explain why the universe appears so quiet. Because if very few civilizations manage to pass through that narrow gateway, then the galaxy might remain mostly silent, even after billions of years. For now, this idea remains only a possibility among many. Scientists continue to search the sky for signals, planets, and subtle signs of life beyond Earth. But as we explore these possibilities, the quietness of the universe begins to feel less like an empty void and more like a story still waiting to unfold. A story about life, intelligence, and the delicate path that leads from simple atoms to beings capable of asking questions about the stars. And as we follow that path further back into the history of life itself, we begin to see just how remarkable and perhaps how rare that journey may truly be. When we imagine alien civilizations, our minds often drift toward dramatic images. Vast cities glowing on distant planets, giant spacecraft crossing the darkness between the stars, powerful radio signals echoing across the galaxy like cosmic lighthouses. But there is another possibility that scientists sometimes consider, and it leads in a quieter direction. What if advanced civilizations do exist somewhere nearby, yet their technology is so subtle that we simply do not recognize it? On Earth, technological progress often moves toward efficiency and miniaturization. Machines that once filled entire rooms can now fit inside a pocket. Computers that once required entire buildings now exist as tiny chips hidden inside everyday devices. As technology improves, it frequently becomes smaller, quieter, and more efficient. Now imagine that trend continuing for thousands or even millions of years. A civilization far older than ours might develop machines that are extraordinarily compact and precise. Their instruments might operate using extremely small amounts of energy. Their communications might be carefully directed rather than broadcast loudly into space. From our perspective, such technology might blend almost perfectly into the natural background of the cosmos. In fact, some scientists have suggested that alien machines could exist within our own solar system without us noticing. To understand how this might be possible, consider the scale of space around us. The region surrounding Earth extends far beyond our planet and the Moon. It includes millions of asteroids, countless fragments of rock, and vast empty spaces stretching between the planets. Even within our own solar system, there are many places where small objects can drift quietly for millions of years. If a robotic probe from another civilization were drifting among these rocks, it might not look very different from a natural asteroid. It might not be enormous or glowing with obvious signs of artificial construction. Instead, it could be modest in size, perhaps no larger than a small spacecraft or even a compact device. Some researchers have playfully imagined probes no larger than objects we already carry in our daily lives. Something the size of a handheld device might be, perfectly capable of observing a planetary system, collecting information, and transmitting data quietly back to its creators. Such a probe could rest on the surface of an asteroid or orbit silently around a distant planet. Unless we happen to examine it very closely, it might appear to be nothing more than another piece of space debris drifting through the solar system. To illustrate this idea, imagine a small group of ants walking across a forest floor. Nearby sits a parked automobile. From the perspective of the ants, that automobile is far beyond their understanding. They may climb across its surface without realizing that it is a machine designed for travel. The ants experience the object as part of their environment rather than recognizing it as advanced technology. In a similar way, it is possible that humans could encounter alien technology without immediately recognizing it as artificial. Our expectations about alien machines often involve enormous structures or bright signals, but advanced engineering might actually move in the opposite direction, toward designs that are subtle and efficient. A probe observing our solar system might operate quietly, sending occasional bursts of information toward distant stars using highly focused communication beams. It might draw energy from sunlight or cosmic radiation. Its presence might be almost indistinguishable from natural objects unless we examined it closely. There is another reason why advanced technology might remain hidden. Civilizations capable of interstellar travel might also be cautious. Broadcasting powerful signals in every direction could reveal their presence to unknown observers. Instead, they might choose to communicate only with specific targets, using narrow signals that do not spread widely across space. If that were the case, then most of their communications would pass silently through the galaxy without ever reaching Earth. From our perspective, the universe would still appear quiet. These possibilities remind us that the absence of obvious signals does not necessarily mean the absence of intelligence. It may simply reflect the limitations of our current methods of observation. Humanity has only been searching for extraterrestrial signals for a few decades. Our telescopes have grown powerful, and our instruments have become remarkably sensitive, but the cosmos is enormous and filled with countless places where small technologies could remain unnoticed. In other words, the silence we observe may not mean that the galaxy is empty. It may simply mean that we are still learning how to listen. Yet there is another idea that makes the mystery even more intriguing. Even if alien technologies are subtle and difficult to detect, there are certain kinds of exploration that might eventually become visible on a much larger scale. Some scientists have proposed that civilizations could spread across the galaxy using machines designed to reproduce themselves. These explorers would not need to be large or dramatic at first. They could begin as simple robotic probes traveling patiently between nearby stars. But once they reach new worlds, they might build additional machines and continue the journey outward. And if that process continued long enough, it could slowly spread across enormous distances. Which raises a fascinating question. If such exploration is possible, and if the galaxy has had billions of years for civilizations to arise, why do we not see clear evidence of such explorers today? That question leads us to one of the most intriguing ideas in the study of cosmic civilizations, the possibility that even a single society could eventually spread its presence across the stars. When we imagine journeys between the stars, our thoughts often leap immediately toward fast spacecraft and dramatic voyages across enormous distances. Science fiction frequently shows sleek ships crossing the galaxy in days or weeks, effortlessly, leaping from one star to another, but the real universe may not require such speed for exploration to occur. In fact, some scientists have pointed out that even very slow journeys between stars could eventually allow a civilization to spread across large regions of the galaxy. The key idea is patience, combined with a clever use of machines. Imagine a robotic explorer designed for a very specific purpose. Its task is not simply to visit another star system, but to begin a chain of exploration that continues long after the first journey is complete. Such a machine might be sent toward a nearby star carrying tools, instructions, and the ability to use raw materials found in space. The journey itself might take many hundreds or thousands of years, drifting quietly through the darkness between stars. For a human traveller, such a voyage would be impossibly long. But for a machine built to endure, time may not be an obstacle. It could move slowly and patiently, guided by simple instructions, and powered by durable energy systems. Eventually, after a long passage through interstellar space, the probe would arrive in another star system. There it might encounter familiar cosmic scenery, rocky asteroids drifting in silent orbits, frozen moons circling distant planets, clouds of dust and ice left over from the formation of that system billions of years ago. Within those materials lie the ingredients for construction. If the probe were designed with enough sophistication, it could begin gathering resources from these objects. Metals could be extracted from rocky bodies. Ice could provide water and useful chemicals. Energy from the nearby star could power machines and manufacturing systems. Over time, the original probe might build new explorers. These new machines would not need to be large or complicated. Each one might simply carry the same instructions as the original: travel to another nearby star, gather resources, and construct more explorers once you arrive. In this way, the process of exploration could slowly multiply. One probe becomes 2, 2 become 4, 4 become 8. Each generation of machines spreads outward a little farther into the galaxy. This pattern is often described using the concept of self-replicating probes. The phrase may sound technical, but the underlying idea is simple. Machines capable of making copies of themselves using materials they find along the way. A gentle way to imagine this process is to picture seeds drifting through a forest carried by the wind. When one seed lands in fertile soil, it grows into a tree. That tree eventually produces many more seeds, which scatter outward to new locations. Over many seasons, the forest gradually expands, spreading across the landscape. In a similar way, robotic explorers could spread slowly from star to star. The journey between neighbouring stars might take thousands of years, but once a new system is reached and new machines are constructed, the exploration continues, outward again. Each step is slow, but the pattern of growth continues. Over very long periods of time, this process could cover enormous distances. Even if each new generation of probes required thousands of years to reach the next star, the expansion might still spread across large portions of the galaxy within tens of millions of years. On human timescales, tens of millions of years sounds unimaginably long. Entire mountain ranges can rise and erode away in such spans of time. Species evolve, climates shift, and continents drift across the surface of planets. But compared to the age of the Milky Way galaxy, tens of millions of years is surprisingly brief. Our galaxy has existed for more than 10 billion years. That means there has been ample time for civilizations to arise, develop technology, and potentially begin exploring the stars. If even one civilization somewhere in the Milky Way had begun sending out self-replicating explorers millions of years ago, those explorers might already have visited many regions of the galaxy. And this is where the mystery becomes particularly interesting. If such exploration is possible, even slowly, then we might expect to see signs of it. Perhaps unusual objects drifting through star systems. Perhaps machines quietly studying planets. Perhaps traces of ancient probes left behind during earlier stages of exploration. Yet when we examine our own solar system, everything appears natural. The planets follow their predictable paths around the sun. The asteroids move along quiet orbits. Comets glide through the outer darkness of the solar system exactly as gravity predicts. We do not observe clear evidence of alien explorers building machines among the asteroids or quietly surveying our planet from hidden stations. This absence of evidence does not prove that such explorers have never existed. It is possible that they are rare, or that their designs are extremely subtle. But the idea of self-replicating exploration makes the silence of the universe feel even more puzzling. Because if civilizations can spread gradually through the galaxy using patient machines, then even a single society might eventually leave traces across enormous distances. And yet, as far as our observations reveal, The Milky Way still appears calm and undisturbed. The stars burn steadily. The galaxies drift silently through space. The cosmic landscape unfolds exactly as natural processes predict. So we're left with a deeper question. If intelligent civilizations can arise, and if technology might eventually allow them to explore the stars, then why does the galaxy still appear so quiet? Some scientists believe the answer may lie not in the distances between stars, but in the delicate and uncertain path that leads from simple life to advanced civilizations. Because the journey from chemistry to consciousness may be far more difficult than we once imagined, and if that journey rarely succeeds, then the quietness of the universe may begin to make a little more sense. When we look out across the galaxy, it is tempting to imagine that planets like Earth must be common. After all, modern astronomy has revealed that planets form naturally around many stars. Some systems contain giant gas worlds, others contain rocky planets, and a surprising number of stars appear to host several planets at once. From a distance, it might seem that Earth is simply one more example among countless similar worlds. But when scientists look closely at the history of our planet, they begin to notice something remarkable. The emergence of life on Earth did not depend on just one fortunate condition. Instead, it required an extraordinarily long chain of stability, one that lasted for billions of years. That stability is easy to overlook because we experience it every day. The sun rises and sets with dependable rhythm. The oceans remain liquid. The climate changes slowly enough that life can adapt. Yet from a cosmic perspective, this calm environment is far from guaranteed. Earth formed roughly 4.5 billion years ago from a swirling disk of gas, dust and rocky debris surrounding the young sun. In those early ages, the solar system was a much more chaotic place than it is today. Asteroids collided frequently. Planets were still migrating through their orbits, and the surfaces of young worlds were often molten and violent. Life could not appear immediately in such conditions. It required time for the planet to cool, for oceans to form, and for chemistry to begin weaving together the first fragile molecules that would eventually become living systems. Once life began, however, another challenge emerged. Life had to survive. And survival on a planetary scale means maintaining stability across enormous spans of time. For billions of years, Earth has remained within a narrow range of conditions where liquid water can exist. If our planet had been slightly closer to the Sun, its oceans might have evaporated into thick clouds of steam. If it had been slightly farther away, those oceans might have frozen solid beneath a permanent crust of ice. Instead, Earth has remained within a comfortable region around the Sun, a distance where temperatures allow water to remain liquid across much of the planet's surface. Scientists sometimes describe this region as the habitable zone of a star, meaning a place where conditions might allow oceans to exist. But distance from the Sun is only one part of the story. Our star itself has also been unusually steady. Many stars in the galaxy are far more volatile than the Sun, producing intense bursts of radiation or violent stellar eruptions that could strip away a planet's atmosphere. The Sun, by contrast, has provided relatively stable energy for billions of years. Its light has warmed the Earth consistently enough that oceans could persist and life could slowly evolve. Even beyond our solar system, the galaxy itself contains regions that are more dangerous than others. Closer to the centre of the Milky Way, stars are packed much more tightly together. Supernova explosions occur more frequently, bathing nearby planets in intense radiation. Gravitational disturbances from neighbouring stars can disrupt planetary systems, sending worlds drifting from their original orbits. Our solar system happens to reside in a quieter neighbourhood of the galaxy, far enough from the crowded centre to avoid many of these dangers. And then there are the countless collisions that have shaped the history of planets. large asteroids and comets have struck Earth many times in the distant past. Some of those impacts caused massive extinctions, reshaping the course of evolution. One famous impact 66 million years ago contributed to the disappearance of the dinosaurs. Yet despite these catastrophic events, life on Earth never vanished entirely. The evolutionary story was interrupted many times, but it was never completely erased. Imagine a candle burning steadily through a long night. Occasionally, a sudden gust of wind might cause the flame to flicker or shrink, but somehow through every disturbance the flame continues to burn. In a similar way, life on Earth has endured countless challenges across billions of years. There is one more quiet feature of our planet that may have played an important role in this long stability. Earth possesses an unusually large moon. Our moon formed long ago when a young planetary body collided with the early Earth, sending debris into orbit that eventually gathered together into the familiar companion we see in the night sky. Beyond its beauty, the moon also performs a subtle task. It helps stabilize the tilt of Earth's rotation. Without this stabilizing influence, our planet's axis might wobble chaotically over long periods of time. Such variations could produce extreme climate swings that make it difficult for complex life to evolve. Instead, Earth's tilt has remained relatively stable, allowing seasons to occur in predictable patterns over millions of years. When scientists place all of these pieces together, the stable star, the safe region of the galaxy, the presence of liquid oceans, the endurance of life through impacts, and the stabilizing influence of the moon, they begin to see how delicate this long chain of stability may be. None of these conditions alone guarantees the emergence of intelligence, but together they create an environment where life has the opportunity to experiment, adapt, and evolve over immense stretches of time. And those stretches of time are essential. On Earth, it took billions of years for life to progress from microscopic organisms to complex creatures capable of building tools, forming societies, and asking questions about the universe. If any part of this long story had been interrupted too severely, if the oceans had disappeared, if the climate had become permanently unstable, or if life had been wiped out completely, the evolutionary journey might have ended before intelligence ever appeared. This realization leads to a quiet and profound possibility. Perhaps planets that remain stable for billions of years are extremely rare. Many worlds may briefly host life before losing their oceans or atmospheres. Others may experience catastrophic disruptions that reset the evolutionary clock again and again. If long planetary stability is unusual, then the emergence of intelligent civilizations may also be far rarer than we once imagined. And that possibility brings us closer to understanding why the galaxy might appear so quiet. Because before civilizations can build technology, send signals, or explore the stars, something much more delicate must occur first. Life must endure. It must persist through billions of years of cosmic change, surviving long enough for evolution to slowly climb from simple cells to complex minds, and that slow climb may be one of the most fragile journeys in the entire universe. After reflecting on the fragile stability of Earth, another quiet possibility begins to emerge. Perhaps the rarity of intelligent life does not depend only on the properties of a single planet. Instead, it may depend on the structure of an entire planetary system. In other words, the question may not simply be whether Earth is rare. The deeper question might be whether solar systems like ours are rare. At first glance, our solar system may appear ordinary. A star sits at the center, surrounded by planets that move along predictable paths. Some of those planets are small and rocky, while others are large gas giants with thick atmospheres and swirling storms. But as astronomers have discovered more planetary systems around other stars, they have begun to notice something surprising. Many planetary systems look very different from our own. Some contain enormous planets orbiting extremely close to their stars. These worlds, often called hot Jupiters, circle their stars in just a few days. Their surfaces are blasted by intense radiation and heat, creating environments far more extreme than anything found in our solar system. Other systems appear chaotic, with planets following highly stretched orbits that swing dramatically closer to and farther from their stars. In such systems, gravitational disturbances may occur frequently, disrupting the long-term stability of smaller planets. By contrast, our solar system is unusually calm. The planets move along nearly circular paths around the Sun, maintaining stable distances for billions of years. This kind of orbital stability allows climates on planets like Earth to remain relatively predictable over long stretches of time. A stable orbit means that the amount of sunlight reaching Earth changes slowly and gradually, giving life the opportunity to adapt rather than face sudden environmental extremes. Another important feature of our solar system lies far beyond Earth. Orbiting at a great distance from the Sun are the giant planets: Jupiter, Saturn, Uranus, and Neptune. These enormous worlds contain most of the planetary mass in our system, and their gravitational influence quietly shapes the motion of smaller objects. Jupiter in particular may play an important role. Because of its immense gravity, Jupiter acts as a kind of cosmic guardian, altering the paths of many comets and asteroids that wander through the outer solar system. Some objects are pulled inward toward the Sun, while others are flung outward into deep space. Although Jupiter cannot prevent all impacts on Earth, its presence may reduce the number of large objects that reach the inner planets. In this sense, the giant planets may help maintain the long-term stability of the inner solar system, creating a calmer environment where life can evolve. There is also the quiet influence of our moon, which we briefly mentioned earlier. Earth's moon is unusually large compared to the size of our planet. Most moons in the solar system are tiny companions orbiting much larger planets, but the moon is different. It is large enough to exert a stabilizing influence on the tilt of Earth's rotational axis. That tilt, roughly 23 degrees relative to our orbit around the Sun, is what creates the changing seasons on Earth. Over very long periods of time, gravitational forces from other planets could cause that tilt to vary unpredictably. If Earth's axis tilted wildly back and forth, the climate could shift dramatically from one era to another. Ice ages might become far more extreme, while tropical regions might swing rapidly into freezing conditions. The presence of the moon helps steady this tilt, keeping Earth's rotation relatively stable over millions of years. As a result, the seasons remain consistent enough for ecosystems to adapt gradually, rather than face constant upheaval. When scientists step back and consider all these factors together, the stable orbit, the presence of giant planets, the influence of the moon, and the relatively quiet region of the galaxy where our solar system resides, they begin to wonder whether this combination may be unusual. Perhaps many planets in the galaxy possess oceans and atmospheres, but if their orbits are unstable, or if their planetary systems are chaotic, those environments might change too quickly for complex life to emerge. Imagine trying to grow a delicate garden in a place where the climate swings unpredictably between scorching heat and deep freeze. Plants might sprout briefly, but long-term ecosystems would struggle to survive. Similarly, complex life may require not only the presence of water and energy, but also the quiet consistency of environmental conditions over billions of years. In that sense, the evolution of intelligence may depend on a remarkable level of patience from the universe. Life must be given time, vast stretches of time, to experiment with new forms, develop new structures, and gradually increase in complexity. If the surrounding planetary system remains stable during that time, evolution can slowly climb upward from simple organisms toward more complex creatures. But if the environment changes too violently or too often, the evolutionary process may be interrupted again and again before it reaches those higher levels of complexity. This idea is sometimes described as the rare Earth hypothesis. It suggests that while simple life might exist on many planets, the precise conditions required for complex life may be far less common. In other words, microbial life might be scattered widely across the galaxy, quietly inhabiting oceans beneath alien skies. But planets capable of supporting long uninterrupted evolutionary journeys from microbes to intelligent beings might be far rarer. If this possibility is correct, then the silence of the universe may begin to feel less mysterious. There may indeed be life on many distant worlds, but most of it could remain simple, microscopic, and hidden beneath alien oceans. The step from microbes to minds may require an extraordinary chain of stability that only a few planets ever experience. And even if a world manages to preserve that stability long enough for complex organisms to evolve, another long climb still remains ahead. Because the journey from simple life to intelligent beings is not a single step. It is a slow ascent across billions of years of evolutionary experimentation, and that ascent may involve one of the most remarkable transformations in the history of life. The moment when simple cells first became something far more complex. When we imagine life on other worlds, it is easy to picture creatures walking across alien landscapes, or perhaps intelligent beings looking up at unfamiliar constellations. But the truth is that life does not begin that way. The story of life begins in a far quieter form. On Earth, the earliest life we know of was microscopic. Tiny organisms, invisible to the naked eye, drifting through ancient oceans. These early forms of life appeared surprisingly early in Earth's history, perhaps within a few 100 million years after the planet cooled enough for oceans to exist. From a cosmic perspective, that was relatively quick. Once the conditions were right, liquid water, a stable surface, and a rich mixture of chemicals, life seems to have emerged rather readily. That observation has led some scientists to wonder whether the origin of life might be a common event in the universe. Perhaps on many planets with oceans and the right chemistry, simple life appears naturally. But what happened next on Earth tells a very different story. For an extraordinarily long time, almost 2 billion years, life on our planet remained simple. These early organisms were single cells. They lived, reproduced, and evolved slowly over immense stretches of time. Some developed the ability to capture energy from sunlight, gradually filling Earth's atmosphere with oxygen. Others adapted to extreme environments, thriving in volcanic vents beneath the sea or within sediments deep below the ocean floor. Yet despite all this activity, life remained microscopic. No forests, no animals, no complex ecosystems filled the planet. The oceans were dominated by tiny cells drifting quietly through ancient waters. Then, at some point roughly 2 billion years ago, something remarkable happened. A new kind of cell appeared. These cells were far more complex than the earlier forms of life. Instead of being simple structures, they contained internal compartments that allowed different chemical processes to occur simultaneously within the same cell. In the center of these cells was a specialized structure that stored genetic information, acting as a kind of control center for the cell's activities. Around it were tiny structures responsible for producing energy, building proteins, and carrying out other essential functions. In simple terms, these were complex cells with internal structures that allowed them to perform many tasks at once. Today, every plant, animal, and fungus on Earth is built from this type of cell. Even our own bodies, trillions of cells working together, depend on this remarkable cellular architecture. But here is the curious part of the story. As far as scientists can tell, this transformation from simple cells to complex cells may have happened only once in the entire history of life on Earth. For billions of years before that moment, life remained simple, and after that moment, complex life gradually flourished. This suggests that the transition from simple cells to complex ones may have been an extremely rare evolutionary event. Some researchers believe that this step required a very unusual biological partnership. According to one widely accepted idea, a small organism capable of producing energy entered into a larger cell and began living inside it. Instead of being digested, the smaller organism remained there, providing energy for the host cell. Over time, the two organisms became inseparable, forming a new kind of living system. The descendants of that ancient partnership still exist today within every complex cell in our bodies. If this event truly occurred only once in Earth's long history, it raises an intriguing possibility. Perhaps the evolution of complex cells is one of the most difficult steps in the entire chain leading to intelligent life. Simple life might emerge relatively easily on many planets. Microorganisms could populate oceans beneath alien skies across the galaxy. But the step toward complex cellular structures, those intricate living systems capable of forming tissues, organs, and eventually brains, might be extraordinarily rare. Without that step, evolution may never produce animals, forests, or intelligent beings capable of building technology. The planet would remain inhabited only by microscopic life, quietly carrying out chemical processes for billions of years without ever developing the structures needed for complex ecosystems. When we view Earth's history through this lens, the rise of complex life begins to feel less inevitable. For more than half of our planet's existence, life remained microscopic. Only after the appearance of complex cells did evolution begin producing larger organisms, creatures with multiple cells cooperating together in organized structures. From there, the pace of evolution gradually accelerated. Plants spread across land. Animals developed nervous systems. Eyes, limbs, and brains evolved through countless generations of adaptation. Eventually, one branch of that long evolutionary tree produced beings capable of language, culture, and technology. But the journey from the first simple microbes to thinking minds required an astonishing amount of time. Billions of years passed between those early oceanic microorganisms and the appearance of intelligent beings capable of asking questions about the universe. This slow climb from microbes to minds may represent one of the greatest filters in the cosmic story of life. If the emergence of complex cells is extremely rare, then most life in the universe may remain forever microscopic. Planets might teem with microbial ecosystems while never producing forests, animals, or civilizations. In that case, the silence of the galaxy would begin to make sense. The universe might indeed be full of life, but most of that life could be too small, too simple, and too quiet to ever build telescopes or send signals across the stars. And the few planets that do manage to climb the long evolutionary ladder toward intelligence must still pass through yet another set of challenges. Because even when complex life appears, the emergence of technological civilizations is not guaranteed. The next part of our story explores that possibility. It asks whether intelligent civilizations may appear from time to time across the galaxy, but exist only briefly, like fleeting sparks in the vast darkness of cosmic time. When we reflect on the immense history of the universe, it is easy to imagine civilizations spreading slowly across the stars, growing older and wiser over millions of years. In that vision, intelligent beings might travel between worlds, build vast networks of communication, and gradually explore the entire galaxy. But there is another possibility, one that is quieter and perhaps more fragile. It is the idea that civilizations may appear only briefly. To help explain this possibility, astronomer Frank Drake once used a gentle and memorable comparison. He suggested that civilizations might resemble rare orchids in a forest. An orchid spends most of its life hidden. For long stretches of time, nothing appears above the surface. Then, suddenly and quietly, a flower blooms. It is delicate, intricate, and beautiful. But the bloom does not last forever. After a short time, the flower fades again, leaving little trace that it was ever there. Civilizations, Drake suggested, may behave in a similar way. Across the galaxy, intelligent societies might arise from time to time. They may develop language, science, and technology. For a brief period in the long history of their planets, they might look up at the stars and begin to wonder whether anyone else is out there. But the duration of that phase, the period when a civilization possesses technology capable of exploring or communicating across the cosmos, may be surprisingly short. To understand this idea, it helps to step back and consider the enormous scale of cosmic time. The Milky Way galaxy has existed for more than 10 billion years. During that time, countless stars have formed and faded. Planets have assembled from clouds of dust, and many of those worlds may have hosted oceans and atmospheres where life could begin. If intelligent civilizations appear from time to time during this vast span, they may still remain incredibly rare when viewed across billions of years. Imagine a dark field on a summer night where tiny fireflies flicker briefly in the distance. Each light appears for a moment, glows softly, and then disappears again into the darkness. If you glance at the field at any single instant, you may see only a few lights, or perhaps none at all, even though many fireflies are quietly moving through the night. In a similar way, civilizations may appear as brief sparks in the immense darkness of cosmic time. One society might emerge on a distant world, flourish for a few thousand or perhaps a few 100,000 years, and then vanish long before another civilization arises elsewhere. Because the galaxy is so old, these sparks may rarely overlap. A civilization that flourished 1 million years ago might have disappeared long before another intelligent species even began evolving on its own planet. When the second civilization finally develops, technology, the first may already be nothing more than ancient ruins scattered across an abandoned world. If that pattern is common, the galaxy could contain many civilizations across its history, but almost none existing at the same moment. This idea offers a simple explanation for why the universe appears so quiet. This silence may not mean that intelligence has never appeared elsewhere. Instead, it may reflect the briefness of technological civilizations compared with the enormous age of the galaxy. Human civilization itself offers a striking example. Modern technology, radio transmitters, satellites, computers, and spacecraft, has existed for only a tiny fraction of our planet's history. Radio communication began little more than a century ago. Space exploration started only in the middle of the 20th century. If our technological phase lasts only a few centuries, or a few thousand years, it would represent an almost invisible moment on the cosmic timescale. To visualize this, imagine compressing the entire 10 billion year history of the Milky Way into a single calendar year. In that scale, the appearance of human radio signals would occur in the final seconds before midnight on the last day of the year. If other civilizations experience similar brief periods of technological activity, their signals may simply occur at different moments in this vast cosmic calendar. They may rise and fall without ever overlapping with ours. Another possibility is that civilizations may change in ways that make them harder to detect. After a brief period of broadcasting signals into space, they might shift toward quieter technologies, communication methods that do not leak detectable energy across the galaxy. Over time, their presence could become increasingly subtle, blending into the background of natural cosmic processes. In that case, the visible phase of a civilization, the time when it produces strong radio signals or large technological structures, might be even shorter. For a brief moment, a civilization shines brightly, like an orchid in bloom. Then it fades back into the quiet background of the universe. When astronomers search the skies for signs of intelligent life, they're essentially looking for these brief blossoms. They are listening for signals that may appear only during a narrow window in the long history of a civilization. If that window is short, and if civilizations are scattered sparsely across the galaxy, then the chances of two technological societies existing at the same time may be very small. This does not necessarily mean that intelligence is impossible elsewhere. It may simply mean that the timing must be extraordinarily lucky. Two civilizations must arise not only in the same galaxy, but within overlapping slices of cosmic history. And that overlap may be rare. The orchid analogy reminds us that the appearance of intelligence may be delicate and temporary. Civilizations may bloom, glow softly for a moment in cosmic time, and then fade again into silence. And if that pattern is common across the universe, it would help explain why the Milky Way, despite containing hundreds of billions of stars, still appears so quiet when we listen for voices among the stars. The galaxy may not be empty, but the moments when civilizations shine brightly enough to be noticed may be brief, fragile, and separated by vast oceans of time. If civilizations sometimes bloom like rare orchids, appearing briefly in the long darkness of cosmic time, an important question naturally follows. Why might those blooms be so short? One possibility is that the period when a civilization develops powerful technology may also be the most dangerous phase of its entire history. In the early stages of civilization, a species may live for thousands of years with relatively limited tools. Communities grow, knowledge accumulates slowly, and the surrounding environment changes gradually. But eventually, something different begins to happen. Scientific understanding grows, technology advances, and suddenly a civilization finds itself holding tools capable of transforming an entire planet. For humanity, this transformation began only recently. For most of our history, human societies were limited by the pace of natural processes. Travel was slow, communication was local, and the power available to individuals was relatively small. Then, over the course of only a few centuries, the pace of change accelerated dramatically. The discovery of new sources of energy, the development of complex machines, and the rise of global communication networks allowed human civilization to reshape landscapes, alter ecosystems, and influence the atmosphere itself. These achievements are remarkable expressions of intelligence and creativity. But they also reveal something important about the stage of development that civilizations eventually reach. At a certain point, a society becomes powerful enough to affect its entire world, and when that moment arrives, the same tools that enable progress may also carry risks. One of the clearest examples appeared in the 20th century with the development of nuclear weapons. For the first time in Earth's history, a single species created devices capable of releasing enormous amounts of energy in an instant. These weapons demonstrated that technological power could grow to levels where the survival of civilization itself might be placed in danger. Fortunately, despite moments of tension and uncertainty, humanity has so far avoided the large-scale use of such weapons since the middle of the 20th century. But the existence of these technologies reminds us that knowledge can advance rapidly, sometimes faster than the social systems designed to manage it. And nuclear technology is only one example. Modern science has opened doors in many fields, including biology, artificial intelligence, and advanced engineering. These areas hold extraordinary promise for improving human life. At the same time, they illustrate a broader challenge faced by any intelligent civilization. The ability to manipulate the world grows steadily more powerful. With advances in biological science, for example, Researchers now understand how to alter the genetic instructions that guide living organisms. These tools offer the possibility of curing diseases and improving agriculture. But they also demonstrate that life itself can be modified in ways that carry unpredictable consequences if used carelessly. Similarly, advances in computing and artificial intelligence allow machines to perform tasks once thought possible only for human minds. These technologies may help solve complex problems in medicine, climate science, and engineering. Yet they also raise new questions about how society should guide and regulate systems that may become increasingly autonomous. In each case, the underlying pattern is similar. Knowledge expands, power increases, and with that power comes responsibility. The challenge faced by a young technological civilization is learning how to manage this rapidly growing influence without allowing it to spiral beyond control. An image that sometimes helps illustrate this moment is the idea of a child sitting at the controls of a powerful machine. The machine itself may be capable of remarkable things. It can move enormous weights, reshape landscapes, or travel great distances. But without careful guidance, it can also cause harm. In the early stages of learning, mistakes are possible. In the same way, civilizations may pass through a phase where their technological abilities grow faster than their collective wisdom. Scientific discovery can proceed at breathtaking speed, while social understanding and global cooperation evolve more slowly. If that imbalance becomes too large, a civilization may struggle to navigate the risks created by its own inventions. Some thinkers have suggested that this stage may represent a common challenge faced by intelligent species throughout the universe. When a civilization first discovers the deeper laws of nature, it unlocks tremendous power. Energy can be released from matter, chemical processes can be redesigned, and machines can begin to replicate tasks once performed by living minds. Each discovery opens new possibilities, but it also requires new forms of responsibility and cooperation. If a civilization fails to develop those systems of guidance quickly enough, the technologies themselves may become sources of instability. This possibility leads to a quiet and sobering thought. Perhaps many civilizations reach the stage where their knowledge allows them to reshape their planet. But only some succeed in navigating the dangers that accompany that power. Those that manage to guide their technologies wisely may continue exploring the stars, gradually expanding their presence across the galaxy. Those that fail may experience disruptions that bring their technological era to an abrupt end. From the perspective of distant observers, the difference between these outcomes might appear as silence. A civilization might briefly produce powerful signals, radio transmissions, spacecraft launches, and other detectable technologies. Then, if that society does not survive the challenges of its own inventions, those signals may fade again. The stars would continue shining as they always have. The planets would continue orbiting their suns. But the brief technological voice that once emerged from that world would disappear. If such moments occur throughout the galaxy, the pattern might resemble the faint echoes of many civilizations rising and fading across cosmic history, each one reaching a point where its knowledge becomes powerful enough to reshape its world, each one facing the delicate challenge of learning how to use that power wisely. And the fate of each civilization may depend on how successfully it navigates that narrow and uncertain stage of its development. In the previous part of our journey, we explored how civilizations may eventually develop technologies powerful enough to reshape their entire world. But the challenge of survival may not depend only on the tools themselves. A deeper difficulty may lie in something more subtle, the ability of a civilization to manage those tools wisely. Because knowledge often grows faster than the systems designed to guide it. Throughout human history, scientific discovery has moved forward with remarkable speed. New ideas appear, experiments reveal unexpected truths about nature, and technologies emerge that transform the way societies function. Yet the development of shared understanding, political cooperation, cultural adaptation, and long-term planning often unfolds much more slowly. This difference in pace creates a delicate imbalance. Imagine a civilization walking across a narrow bridge suspended high above a valley. The bridge represents the path of technological progress. Each step forward brings new possibilities, new energy sources, new medicines, new machines capable of solving complex problems. But the bridge is narrow, and the landscape around it is unfamiliar. Moving too quickly without careful coordination could lead to instability. For a civilization to cross safely, its members must learn how to cooperate on a scale far larger than anything required before. Human history provides several quiet reminders of how difficult this coordination can be. During the 20th century, there were moments when misunderstandings and technical errors nearly led to catastrophic consequences involving nuclear weapons. In a few cases, warning systems mistakenly indicated incoming attacks, and only the calm judgment of individuals prevented escalation. These moments rarely receive as much attention as dramatic historical events, yet they illustrate how complex technological systems can create situations where small errors might produce enormous consequences. Another example appears in the relationship between human civilization and the natural environment. Over centuries, industrial development allowed societies to build cities, produce energy on large scales, and transport goods across the entire planet. These achievements improved many aspects of human life. But they also introduced new challenges. The same technologies that enabled prosperity also altered Earth's atmosphere, oceans, and ecosystems in ways that were not fully understood at the time. Scientists are still studying the long-term consequences of these changes and exploring ways to balance human activity with the stability of the planet's environment. These situations reveal an important pattern. Technological capability can grow rapidly once a civilization understands the underlying laws of nature. Energy can be extracted from new sources. Biological processes can be modified. Machines can be built to carry out complex tasks with great efficiency. But the wisdom required to manage these capabilities must develop through cooperation, cultural learning, and careful reflection. And those processes can take time. For a civilization that suddenly acquires powerful technologies, the challenge becomes learning how to use them responsibly before unintended consequences arise. This difficulty may not be unique to humanity. Any intelligent species that reaches a similar stage of development might encounter the same delicate moment in its history. Scientific discovery would reveal the deep structure of nature. Energy would become easier to harness. Biological systems could be manipulated. Artificial systems might begin performing tasks once carried out only by living minds. Each breakthrough would expand the civilization's influence over its environment. And with each expansion of power, the importance of cooperation would increase. Because when the actions of one group can affect the entire planet, decisions can no longer remain purely local. They must take into account the long-term stability of the entire world. This requirement introduces a profound challenge. Civilizations must learn not only how to build powerful technologies, but also how to guide them collectively. If cooperation fails, if disagreements, competition, or short-term thinking dominate decision-making, the risk created by advanced technologies may grow faster than the systems designed to manage them. Some scientists and philosophers have suggested that this stage may represent one of the most difficult transitions in the development of intelligent life. Not a physical barrier, but a social and cultural one. The challenge is not discovering the laws of nature. The challenge is learning how to live with the power that those discoveries provide. Returning to the image of the narrow bridge, the journey forward requires careful balance. Each step must be steady. Communication must remain open, and the travellers must recognize that they're all crossing the same bridge together. If enough civilizations fail to maintain that balance, the galaxy might contain many worlds where intelligence appeared briefly, developed powerful tools, and then struggled to manage them safely. From a distance, these civilizations might shine for a short time, broadcasting signals, launching spacecraft, or altering their planets in ways visible across space. But if they did not successfully coordinate the use of their technologies, those signals might fade again. The stars would continue shining quietly, and the evidence of those brief civilizations might gradually disappear. In this way, the silence of the galaxy may not be caused by a lack of intelligence. Instead, it may reflect the difficulty of navigating the moment when knowledge begins to outrun wisdom. That delicate stage may determine whether a civilization continues exploring the universe or whether its brief appearance becomes one more quiet chapter in the long and patient history of cosmic evolution. As we continue exploring the quiet mystery of the universe, the pieces of the puzzle begin to gather together. We have considered several possibilities. Perhaps planets capable of supporting life are rare. Perhaps the path from simple life to complex organisms is extremely difficult. Perhaps civilizations appear only briefly before disappearing again. Each of these ideas offers a partial explanation for the silence of the galaxy, but some scientists have suggested that these pieces may all reflect a deeper principle, one that operates across the entire history of life in the universe. This idea is known as the Great Filter. The phrase may sound dramatic, but the concept itself is quite simple. The Great Filter refers to a stage in the development of life that is extremely difficult to pass. It is a barrier along the long evolutionary road from simple chemistry to advanced civilizations capable of exploring the stars. Imagine the history of life as a long journey along a winding path. At the beginning of that path lies a young planet newly formed, with oceans, minerals, and chemical reactions slowly unfolding in its environment. Somewhere along this path, simple life may appear, tiny cells drifting in ancient seas. Further along, those cells might evolve into more complex forms of life. Organisms grow larger, develop specialized tissues, and eventually form ecosystems of plants and animals. Still farther along the path, intelligence may emerge. Creatures capable of reflection, communication, and curiosity begin to examine their surroundings. They build tools, develop science, and gradually uncover the deeper laws that govern the universe. Eventually, such a civilization might learn how to harness powerful forms of energy, construct spacecraft, and send signals across the vast distances between stars. But along this long road, there may be narrow passages, places where the path constricts into a tight gate. Only a few travellers may manage to pass through these gates successfully. Most journeys may end before reaching the next stage. These narrow passages represent the Great Filter. The idea was proposed as a way to explain the famous question sometimes called the Fermi Paradox, the puzzle of why the universe appears so quiet despite the enormous number of stars and planets that exist. If intelligent civilizations were common, we might expect the galaxy to contain clear signs of their presence. Advanced societies could spread gradually from star to star, sending spacecraft, building large structures, or broadcasting signals detectable across interstellar distances. Given the billions of years available for such expansion, the Milky Way might already be filled with evidence of technological activity. And yet, when we observe the sky, we do not see these signs. The planets move along their natural orbits. The stars burn quietly. The galaxies drift through space according to the predictable laws of gravity. Everything appears peaceful and undisturbed. The Great Filter offers a possible explanation. It suggests that somewhere along the long chain of steps leading from simple chemistry to galaxy-spanning civilizations, there exists a stage so difficult that almost no worlds manage to pass it. This stage could occur very early in the story of life. Perhaps the formation of the first living cells is extremely unlikely, requiring a rare combination of chemistry and environmental conditions. If that were the case, then most planets might remain lifeless despite having oceans and atmospheres. Another possibility is that simple life appears easily, but the evolution of complex cells is extraordinarily rare. As we discussed earlier, the transition from simple cells to the complex cellular structures found in plants and animals may have occurred only once in Earth's history. If that step is exceptionally difficult, many planets might host microbial life without ever producing complex organisms. Still another possibility is that complex life evolves occasionally, but intelligence itself remains rare. Brains capable of reasoning, language, and technological creativity may require a long chain of evolutionary accidents that seldom occur. Or perhaps intelligence appears from time to time, but civilizations rarely survive long enough to expand beyond their home planets. In that case, the Great Filter might lie in the stage we explored in the previous sessions, the delicate moment when technological power becomes great enough to reshape an entire world. The important point is that the Great Filter does not necessarily refer to a single event. It may represent one particularly difficult step, or perhaps several difficult steps scattered along the evolutionary path. Each step acts like a narrowing in the road. Many planets may begin the journey. Fewer may reach the next stage. Fewer still may continue beyond that, and only a very small number may eventually develop civilizations capable of exploring the stars. From a distance, the universe might appear silent, not because life never arises, but because so few worlds manage to pass through all the narrow gates along this long journey. If the Great Filter exists, it shapes the destiny of life across the entire cosmos. It determines whether the universe becomes filled with civilizations or remains largely quiet, with only occasional sparks of intelligence appearing here and there. And as we reflect on this idea, a deeply intriguing question emerges. Where is the Great Filter located? Did it lie somewhere in the distant past, in the ancient stages of life's evolution? Or does it still lie ahead of us, waiting somewhere in the future of our own civilization? The answer to that question carries very different implications for humanity, because if the hardest steps are already behind us, then our existence may represent one of the rare successes in a universe where most journeys never reach this far. But if the Great Filter lies somewhere ahead, then the quietness of the galaxy may be a warning written across the stars, a reminder that the path forward for intelligent civilizations may be more fragile than we realize. Once we begin thinking about the Great Filter, an important question quietly emerges. Where exactly is this difficult barrier located along the long path of cosmic evolution? One possibility is that the hardest steps may already lie far behind us. If this is true, then the silence of the universe might not be a warning about the future. Instead, it may reflect how extraordinarily rare our own existence already is. To understand this idea, it helps to imagine the entire history of life as a sequence of improbable events. Each event must occur before the next one becomes possible. At the very beginning lies the origin of life itself. Somewhere on the young Earth, in ancient oceans filled with dissolved minerals and energy from sunlight or volcanic activity, simple molecules began interacting in increasingly complex ways. Eventually, those interactions may have produced the first structures capable of copying themselves. Once a molecule can make imperfect copies of itself, natural selection begins to operate. Variations appear, and those variations compete. Over time, systems that replicate more efficiently become more common. From that humble beginning, the first living cells may have emerged. Yet scientists still do not fully understand how this transformation from chemistry to biology occurred. It may require a delicate combination of ingredients: liquid water, the right chemical building blocks, sources of energy, and stable environmental conditions lasting long enough for complex reactions to unfold. If the origin of life is extremely unlikely, then most planets, even those with oceans, might never pass this first step. But suppose life does appear. The next challenge is survival. Early, organisms must endure the turbulent conditions of a young planet. Asteroid impacts, volcanic eruptions, and dramatic climate changes can repeatedly threaten fragile ecosystems. Only if life survives these early hazards does evolution gain the time it needs to experiment with new forms. On Earth, life endured, and over billions of years, another remarkable transition eventually occurred. Simple cells evolved into complex cells. As we explored earlier, this transformation may have required a rare biological partnership, one organism living inside another in a cooperative relationship that allowed both to survive more effectively. That partnership produced the cellular architecture that supports every plant, animal, and fungus on our planet today. Without this step, life might have remained permanently microscopic. But even complex cells were not the end of the journey. The next stage involved the emergence of multicellular life, organisms composed of many cooperating cells forming tissues and organs. This step required new forms of biological coordination. Cells had to communicate, specialize, and work together in ways that allowed entire organisms to function as unified systems. Eventually, this evolutionary path produced creatures capable of movement, perception, and increasingly complex nervous systems. Some organisms developed eyes to detect light, limbs to move across land or through water, and brains capable of processing information about their environment. Over immense stretches of time, these systems grew more sophisticated, and finally, on one small planet orbiting an ordinary star, a species emerged capable of reflection. Humans developed language, abstract thought, and the ability to transmit knowledge across generations. Scientific inquiry revealed the laws governing matter, energy, and the cosmos itself. In only a few thousand years, a blink of an eye in cosmic time, human civilization learned to build telescopes, launch spacecraft, and detect planets orbiting distant stars. When we consider this long sequence of events, it becomes clear that each step may represent a rare success. If the origin of life is difficult, that alone would limit how many planets host living systems. If the emergence of complex cells is even more difficult, the number of worlds capable of producing animals or intelligent beings might shrink dramatically. If intelligence itself requires a unique combination of evolutionary pressures, then technological civilizations could be exceedingly rare. In this view, the great filter may lie entirely in the past. The difficult gates along the road of evolution may already have been passed by our planet. Earth may simply be one of the few worlds where the entire chain of improbable events unfolded successfully. If that is true, then humanity may represent an extraordinary outcome in the cosmic story of life. Our existence would not be a common phenomenon repeated across countless planets. Instead, it might be the result of an unusually fortunate sequence of biological and environmental circumstances. This possibility carries a quietly hopeful implication. If the most difficult evolutionary barriers are already behind us, then the future of intelligent life may not be predetermined by hidden cosmic traps. Instead, the silence of the universe would reflect how rarely the long journey from chemistry to consciousness succeeds. The Milky Way might contain countless planets with oceans and atmospheres. Some of those worlds might host microbial life drifting through alien seas, but only a tiny fraction may ever develop forests, animals, or intelligent beings capable of wandering about the universe. In that case, humanity may occupy a very special place in the cosmic timeline. We would be among the few worlds that managed to pass through the narrow gates of biological evolution. The quiet sky above us would not be a sign of inevitable doom. Rather, it would be a reminder of how remarkable our own existence already is. A reminder that on at least one small planet, life endured long enough to become aware of itself and curious about the vast universe beyond. While the idea that the Great Filter may lie behind us carries a certain quiet comfort, there is another possibility that scientists sometimes consider. The most difficult step in the journey of intelligent life may not have happened yet. It may still lie somewhere ahead. If this is true, then the silence of the universe might not be the result of rare beginnings, but of fragile endings. Civilizations might arise across the galaxy from time to time. Intelligent beings may develop science, build cities, and eventually learn how to harness powerful forms of energy. For a brief moment in cosmic history, those civilizations might even begin looking outward, searching the stars for signs of other minds. But before they manage to spread beyond their home planets, something interrupts the story. Civilization fades, and the stars grow quiet again. This possibility does not require dramatic cosmic catastrophes. No supernova needs to destroy the planet. No asteroid needs to erase life completely. Instead, the danger may emerge from within the civilization itself. As we explored earlier, technological progress eventually grants a species the ability to reshape its environment on a planetary scale. Energy systems grow powerful enough to alter climates. Biological knowledge becomes advanced enough to redesign living organisms. Artificial systems begin to perform increasingly complex tasks. Each of these discoveries offers extraordinary opportunities. New medicines can cure diseases. Efficient energy systems can power entire cities. Intelligent machines can help solve problems that once seemed impossible. But powerful tools also carry risks. If they are used carelessly, or if societies fail to coordinate their use effectively, the consequences can ripple outward across the entire planet. One example involves the long-term stability of planetary environments. Industrial activity allows civilizations to produce energy and materials on enormous scales. Over time, however, these activities may alter atmospheric chemistry, ocean temperatures, and ecological systems in ways that are difficult to reverse quickly. If such changes grow too severe, they could disrupt the delicate environmental balance that supports complex life. Another possibility involves biological technologies. As scientific understanding of life deepens, civilizations may gain the ability to modify genetic systems directly. These technologies hold great promise for medicine and agriculture. But if misused, biological tools might also create new forms of risk, organisms or ecological interactions that spread in unpredictable ways. Advanced computing introduces another frontier. Artificial intelligence systems may eventually assist with scientific discovery, economic planning, and environmental management. Their ability to analyze vast amounts of information could help civilizations solve many difficult problems. Yet these same systems might introduce new challenges if their behavior becomes difficult to predict or control. Each of these examples illustrates the same general principle. Technological progress increases both opportunity and responsibility. A civilization that discovers the deeper laws of nature gains extraordinary capabilities. It learns how to transform matter, manipulate energy, and reshape biological systems. but it must also learn how to guide those capabilities wisely. If it fails to do so, the tools created to improve life may instead destabilize the systems that sustain it. This possibility suggests that the most difficult stage in the development of intelligent life may occur precisely at the moment when civilizations become technologically mature. Before this stage, a species has limited power to alter its world dramatically. After this stage, a civilization that has learned to manage its technology successfully may continue advancing, exploring its solar system, and perhaps eventually reaching nearby stars. But in between lies a narrow and uncertain passage, a moment when knowledge expands rapidly, while social coordination, ethical understanding, and long-term planning must struggle to keep pace. If many civilizations fail to navigate this delicate stage, the result would be a universe filled with brief technological experiments, worlds where intelligence appeared, discovered powerful tools, and then vanished before spreading beyond their home planet. From the outside, these civilizations might leave almost no trace. For a short time, they might broadcast signals into space, radio waves, electromagnetic transmissions, or other technological signatures. But once the civilization disappears, those signals fade quickly into the cosmic background. Within a few thousand years, the evidence may become indistinguishable from natural processes. The planet returns to silence, the stars continue shining, and the long cosmic clock keeps moving forward. If this pattern repeats across the galaxy, it could explain why we observe such a quiet universe, despite the enormous number of planets that exist. Civilizations may arise again and again, but few may survive long enough to become interstellar societies. This possibility can feel unsettling at first, yet it also carries an important implication. If the great filter lies ahead, it does not necessarily represent an unavoidable fate. Instead, it may represent a challenge, a test of whether intelligent species can learn to manage their own technological power. The outcome of that test may determine whether a civilization fades quietly from history or continues its journey outward into the wider universe. And at this moment in our own story, humanity stands somewhere along that uncertain path. We have discovered many of the fundamental laws that govern nature. We have begun exploring our solar system and searching for planets around distant stars. But we're still learning how to guide the extraordinary tools that our knowledge has created. The future of intelligent life on Earth may depend on how wisely we navigate this delicate stage of our development, whether we learn to cross the narrow bridge between discovery and responsibility, whether our brief technological bloom becomes only a short chapter in the long history of life, or the beginning of a much larger cosmic journey. After considering the idea of the Great Filter, whether it lies in the distant past or somewhere in the future, another quiet possibility begins to take shape. Perhaps the universe is not empty of life at all. Perhaps life is everywhere. Tiny organisms may drift through oceans beneath alien skies. Microbial ecosystems might flourish on distant worlds, orbiting stars scattered across the Milky Way. In fact, many scientists suspect that simple life may arise relatively easily once the right ingredients are present. Planets with liquid water, stable environments, and the necessary chemical building blocks could provide fertile ground for microscopic organisms to emerge. If this is true, then the galaxy might be filled with countless worlds where life quietly exists at the smallest scales. But the next step, the emergence of intelligent civilizations, may be far rarer. Some physicists and astronomers have suggested that the leap from simple life to advanced technological societies might be so unlikely that it occurs only rarely across an entire galaxy. One scientist who has spoken about this possibility is the physicist Brian Cox. He has sometimes suggested that while microbial life might be widespread, civilizations capable of building technology may be extraordinarily scarce. perhaps even fewer than one per galaxy on average at any given moment in time. To understand how this could be possible, we must again return to the immense scale of cosmic history. The Milky Way contains hundreds of billions of stars. Around many of those stars, planets orbit in silent paths through space. Some of those planets may possess oceans, atmospheres, and climates that allow life to begin. If even a small fraction of those worlds host simple organisms, the galaxy might be teeming with microbial life. But the emergence of intelligent beings capable of building technology requires a long chain of events. Life must survive for billions of years. It must evolve from simple cells into complex organisms. Ecosystems must remain stable long enough for evolutionary experimentation to continue across vast stretches of time. And somewhere along that path, intelligence must appear. A species must develop the capacity for language, cooperation, and abstract reasoning. It must learn to transmit knowledge across generations, building a cumulative understanding of the world. Even after that point, technological civilization does not appear instantly. Thousands of years of cultural development may pass before scientific methods emerge, before mathematics describes the laws of nature, and before machines capable of exploring space are constructed. When we place all these steps together, the path begins to resemble a long series of unlikely successes. Each stage may eliminate many planets from the journey. Some worlds may never develop life at all. Others may host only microscopic organisms that never evolve beyond simple forms. Still others may produce complex ecosystems of plants and animals, but never develop intelligent species capable of building technology. And among the rare worlds where intelligence does appear, civilizations may not last long enough to expand beyond their home planet. When all of these probabilities are combined, the number of civilizations existing at the same time within a single galaxy could become extremely small. It might even be less than one. At first, that phrase may sound confusing. How can there be fewer than one civilization? But in statistics, this simply means that across many galaxies, some may contain a technological civilization, while many others contain none. On average, the number of active civilizations per galaxy could be less than one. In such a universe, intelligent life would still exist, but it would be extraordinarily rare. To visualize this idea, imagine a vast ocean stretching across an entire planet. Across that ocean, islands occasionally rise above the surface. Some islands appear briefly before sinking again beneath the waves. Others remain above the water for longer periods. If you look across the entire ocean at any given moment, you might see only a few scattered islands, or perhaps none at all within your field of view. Yet over long stretches of time, many islands may have risen and fallen across the surface. In the same way, intelligent civilizations might appear sporadically across the Milky Way. Some may rise, develop technology, and eventually fade away. Others may emerge much later on distant planets, orbiting other stars. But because the galaxy is so large and the timing of civilizations may rarely overlap, the sky we observe today could appear almost completely silent. Even if intelligent life exists somewhere else in the Milky Way right now, the distances involved are immense. The nearest technological civilization could be thousands or even tens of thousands of light years away. At those distances, signals might become too faint to detect easily, or they may not have had enough time to reach us yet. Light travels through space at a constant speed, the fastest speed known in the universe, but even light requires time to cross the enormous distances between stars. A signal sent from the far side of the galaxy might take tens of thousands of years to arrive here, so even if other civilizations exist somewhere in the Milky Way today, we may simply be separated by vast distances and vast stretches of time. From our small vantage point on Earth, the galaxy may appear silent not because life is impossible, but because intelligent life is extraordinarily rare and widely separated. A vast cosmic ocean, and perhaps, scattered somewhere within it, a few distant islands of awareness. One of those islands happens to be our own. As we reflect on the possibility that intelligent civilizations may be extremely rare, the silence of the universe begins to feel less like a mystery and more like a quiet invitation to think carefully about our place in the cosmos. For most of human history, people imagined that the universe must be full of other beings like ourselves. Ancient philosophers speculated about countless inhabited worlds. Later generations looked at the stars and wondered whether other civilizations might be watching the same night sky. Even today, the search for extraterrestrial intelligence continues with great curiosity and optimism. Radio telescopes scan distant regions of the galaxy, listening for signals that might reveal the presence of another technological society. Yet so far, the universe has remained remarkably quiet. This silence can be interpreted in many ways. Perhaps civilizations exist but are separated by enormous distances. Perhaps they communicate using technologies we've not yet learned to detect. Or perhaps the journey from simple life to intelligent beings is so difficult that very few planets ever complete it. If that last possibility is true, then humanity may occupy a very unusual position in the cosmic story of life. Our planet may not simply be one example among countless others. Instead, it may represent one of the rare places where life survived long enough to become aware of itself. Imagine the Milky Way galaxy as an immense landscape of stars stretching across hundreds of thousands of light years. Around many of those stars, planets orbit quietly through space. Some of those worlds may host oceans filled with microscopic organisms, others may be barren deserts of rock and ice. Many may lie somewhere between these extremes. But among all those worlds, there may be only a very small number where intelligence has emerged. And among those rare worlds, there may be even fewer where civilizations have developed the ability to study the universe itself. On one of those worlds, our own, life has taken that step. Human beings have learned to observe distant galaxies, measure the motion of planets, and reconstruct the history of the cosmos stretching back billions of years. We have built instruments capable of detecting faint signals from the earliest moments of the universe. We have sent spacecraft beyond the boundaries of our solar system. And perhaps most remarkably, we have developed the ability to reflect on our own existence. The atoms that form our bodies were once forged in ancient stars. The elements within our cells were assembled through cosmic processes unfolding long before Earth existed. Over billions of years, those atoms became part of living systems capable of perception and thought. In a sense, the universe has become aware of itself through the minds of living beings. If intelligent life is rare, then this awareness may be one of the most extraordinary phenomena in the entire cosmos. It would mean that the ability to ask questions about the universe, to explore its mysteries and contemplate its origins, may appear only occasionally across the vastness of space and time. This realization does not imply that humanity is the center of the universe in any physical sense. The Earth is still a small planet orbiting an ordinary star in one galaxy among billions, but the rarity of intelligent life could give our existence a special kind of significance. Not because we are important in a cosmic hierarchy, but because awareness itself may be precious. Every civilization capable of understanding the universe represents a unique chapter in the story of cosmic evolution. Each one carries the accumulated knowledge of its planet's long biological history. Each one has the opportunity to explore the wider universe and preserve the fragile phenomenon of intelligence. If intelligent civilizations are rare, then their survival becomes deeply meaningful. The continuation of knowledge, culture, and understanding may depend on the choices made by the few societies that reach this stage of development. For humanity, This possibility invites a quiet sense of responsibility. The technologies we've developed now give us the power to alter our planet's environment, to explore other worlds, and eventually perhaps to travel beyond our solar system. These capabilities bring with them an opportunity to preserve and extend the presence of intelligent life. If we succeed in navigating the challenges of our technological age, if we learn to manage our power wisely and cooperate across our planet, then humanity may continue its journey into the wider cosmos. In doing so, we would carry with us the accumulated knowledge of billions of years of evolution on Earth. We would become participants in a much larger story, the gradual spread of awareness through the universe. And if we are not alone, then other civilizations may be undertaking similar journeys on distant worlds, each one contributing its own perspective to the unfolding narrative of cosmic exploration. But even if intelligent life is rare, even if Earth represents one of only a few islands of awareness in the Milky Way, the quiet sky above us does not need to feel lonely. Instead, it can serve as a reminder of the remarkable opportunity that life on this planet has been given, an opportunity to explore, to learn, and to preserve the fragile spark of intelligence that has emerged from the long history of the cosmos. As our journey through this question slowly comes to rest, we return to the quiet mystery that started it all. Why does the universe appear so silent? When we first asked this question, it seemed almost paradoxical. The Milky Way contains hundreds of billions of stars. Around many of those stars, planets orbit in silent paths through space. Across the galaxy, there may be oceans beneath alien skies, rocky deserts beneath distant suns, and frozen worlds drifting quietly in the outer darkness of planetary systems. With so many planets, it seems natural to wonder why we do not see clear signs of other civilizations. Throughout our exploration, we've considered several possibilities. Perhaps planets capable of supporting life are rarer than they first appear. Perhaps the long chain of biological events required for complex life is extraordinarily difficult to achieve. Perhaps intelligent civilizations appear from time to time, but exist only briefly, like rare orchids that bloom for a short moment before fading again. Or perhaps advanced societies exist somewhere in the galaxy even now, but are separated from us by distances so vast that their signals have not yet reached Earth. Each of these possibilities offers a different way of understanding the quietness of the cosmos, and yet, despite decades of scientific searching, we still do not know which explanation is correct. The universe remains patient with its secrets. Astronomers continue listening for faint signals drifting through the background of space. Powerful telescopes search for planets around distant stars, examining their atmospheres for subtle hints of chemistry that might indicate life. New spacecraft travel through our own solar system, exploring icy moons and ancient planetary surfaces where microbial life might exist, even within our cosmic neighborhood. Each discovery adds a small piece to the puzzle, but the larger question remains open. The universe may be full of life, quietly evolving on countless distant worlds. Or intelligence may be one of the rarest phenomena in the entire cosmos, appearing only occasionally across billions of years of cosmic history. Both possibilities are astonishing in their own way. If life is common, then the galaxy may be filled with hidden ecosystems waiting to be discovered. If life is rare, then our own existence becomes an extraordinary chapter in the story of the universe. Either way, the silence we observe today may simply reflect how early we are in this search. Human civilization has only recently developed the tools needed to explore the cosmos in detail. Radio telescopes capable of scanning distant regions of space have existed for only a few generations. The search for planets around other stars, once purely theoretical, has only begun in earnest within the last few decades. In cosmic terms, our efforts have barely started. Imagine standing on a vast shoreline at night, listening for voices across a dark ocean. You pause for a few moments, listening carefully. The waves move softly in the distance, but no voices reach your ears. From that brief silence alone, you could not conclude that no one exists on the other side of the ocean. You may simply need to listen longer. The universe may be similar. The stars have been shining for billions of years, and our search has only just begun. Future generations may build instruments far more sensitive than those we possess today. They may detect subtle signals or discover life in places we have not yet explored. Perhaps one day humanity will find evidence of microbial organisms beneath the frozen crust of an icy moon. Perhaps we will detect faint chemical signatures in the atmosphere of a distant planet, suggesting the presence of alien ecosystems. Or perhaps we will discover something even more remarkable, a signal from another civilization, travelling patiently across the darkness between stars. For now, however, the galaxy remains quiet, and in that quietness there is a certain calm beauty. The night sky stretches above us, filled with stars that have burned for billions of years. Around those stars, countless planets continue their silent orbits. On one small world among them, life has evolved the ability to look outward and wonder, to ask questions about the universe, to imagine the possibilities hidden beyond the distant lights of the galaxy. Whether humanity is alone or one among many, the story of intelligence is still very young. Our civilization has existed for only a tiny fraction of cosmic time. The tools we've developed, science, exploration, and cooperation, may allow us to extend that story far into the future. Perhaps one day the galaxy will no longer appear silent. Perhaps the islands of awareness scattered across space will eventually discover one another. But even if that moment lies far in the future, the quiet present remains remarkable, because here, on this small blue planet, beneath a sky filled with ancient stars, the universe has produced something extraordinary, a species capable of listening, capable of wondering, and capable of continuing the search